Hey, we're back. We're going to mess around with a little bit of chapter 4 now. We're moving away from our hyperbolics and our related rates, and now we're going to get into essentially chapter 4 is like, how do we graph? Y'all think you know how to graph, or maybe you don't, but you think you know how to graph from a college algebra or a pre-calculus class, yet there were small little pieces that we just couldn't quite get without looking at software or maybe estimating. Now we can handle everything. We're going to be able to make some pretty badass graphs now. Granted, we have graphing software, so you should really never make a graph by hand. You should just do it in Desmos or something. But we're going to learn how to do it, and this is going to make us much better at being able to read a graph as well. So let's get into it. Let's jump on down, and here's our rules. We're back in algebra right now. This isn't any sort of calculus. This is just straight algebra. So let's see if we can't just make heads or tails of what this is saying. So an absolute maximum. Absolute. Think about the word absolute. Absolutely. There's no contradiction to this. So when we say back here that f of c is greater than or equal to f of x, for all x in the domain, it's just saying that you plug that number in c, whatever it is, maybe 7. You get a max. It's the biggest freaking value. It pops out. Your y value is the biggest out of any other one in there. Or maybe it's just equal to some other ones. Now we move down to the next one, and we're like, well, dude, now an absolute minimum. Well, that's saying that if you plug in your c value, like, hey, how about 0? Plugging in x equals 0 into x squared. You know that parabola? So it'd be way down at the frickin' bottom. Nothing else could be smaller than it for any value of x. We're saying that's going to be the smallest one we could have. So that's absolute. We're talking about frickin' everything. We'll get you some examples in just a second. I'll expect you to hang on just with some words. And now we have the idea of local or relative maximums. So local, right? Think about going back to Sierra College. Remember that when we were on campus? Oh, what a glorious thing, huh? Don't know what you have till it's gone. So let's stay local. You know what I mean? So if we're on campus and we look at the library, I'm pretty sure that the library, I could be wrong. I'm pretty sure it's the tallest building in all of Rockland. Locally, that's the tallest building, the library. Now, is that the tallest building in the world? Hell no. But locally, right around Rockland, near Rockland. So that's what we're going to talk about. It's just little areas. We're going to use the word near. And near sounds really, really, really technical, right? You're probably thinking, like, what the hell does near mean? We'll show you in a second. It's not that big of a deal. So relative or a local maximum. So it's just saying, like, maybe a hill, right? Top of a hill. It's maybe not the top of every hill, but you're at the top of a hill. So we're going to think when we go through this, peaks and valleys. All right? Peaks, local maxes. Valleys, local mins. So there's our definition. And I'll go back and forth local and relative with maximums. Local and relative, same thing. Absolute also has another one. We can also call this global. So I might accidentally call these globals as well. Right? Doesn't that kind of make sense, though? Local, global. Whatever. Let's keep moving. Enough talking. So let's see something. Let's look and talk about what a local max and a min is versus an absolute max. So I'm going to start off with an absolute max. I'm just going to write it as abs max. And we look at this. Now, this domain is cut off. We actually have endpoints here. They don't take off forever. We just got some endpoints here. So what we're looking for the absolute max, and we're going to talk about where it's happening. So let's write this off on the side. Where is the equivalent of what's the x value? X is the address. Okay, that just tells you where it lives. The y value, that's the what. That's what it pops out. So I'm going to name this thing. This is how we don't have to worry about all this nonsense. I'm going to call this thing f of x. And f of x is defined on a closed interval from -1 on up to 4. I'm going to call it F, so when I write in my answer, I'm just going to write F of the address, telling you where we're at. So we look and we're like, well, what's the absolute max means? What's the tippity toppity, the most, the biggest? And that's going to be right here, right? That's going to be right there at -1. That's the tallest thing. It's taller than it is over at 4, right? So we're going to say for our answer, be like, dude, it's at F of -1. Got it. There's our absolute max. Now let's talk about our absolute min. So we're looking for the smallest value. We're going to pop its address on in there. Absolute min. So we look around and we're like, get smaller, smaller, smaller. Like right down here, huh? At x equals 3. So we will pop in that at 3 we have our absolute min. That should make sense. Don't make it anything more than it is. We're just looking, where do we find the lowest frickin' point on the damn graph? Where do we find the highest point on the frickin' graph? That's absolute. There's no talking about it. We can just keep on rolling. Now we get into our next one, which is going to be our local max and our local min. Now there can be multiple of any of these, whether it's absolute maxes, absolute mins. Things like sine and cosine would be a great example of infinitely many local maxes and mins and absolute maxes and mins. But for now, we're going to look at local maxes and mins. Now, a local max and a local min cannot occur at an endpoint. Local max and min can't happen at endpoints. Okay? They got to be something to the left and to the right of it. All right, just by the definition, the way they work. Don't put too much frickin' thought into this. All right, we're just talking about, so local maxes and mins, I like just going with the idea of peaks and valleys. Do you see any frickin' peaks and valleys? So where we can't is we can't have a local min or max at the endpoints, right? Can't be there. So now all we're doing is looking for peaks and valleys. So in green, I'm going to put in any valleys. And then pink, I'm going to put in any peaks. Oh. That's all we're talking about. When we're talking about near, you're like, just close in on some freaking interval to where that thing is the smallest value. Let's jump back up. Where it's the smallest value. I'm going to the minimum. The smallest freaking value near some C. But that means it has to be some sort of interval when we write this. So this gets a little bit funky. We'll be like, just make some sort of interval. So if we're talking on the max, we're like, look. That point right here is bigger than everything else in that little freaking interval. So that's what we're going to call our local max. Let's put it in there. We're going to say that this thing, that's f of, and we look, where's the address? That's at 1. All right, cool. Well, we found our local max. That's the only one. It's the only peak I can find. So now we go to our local min. So we go look for our local mins, and those are in green. So we just look and we're like, well, there was 2 different valleys. There's 2 different places where it could have held water. Huh? 2 spots like that. So we say f of 0 is a local min. And then we go over and we see our other address. We're like, where was that? Where was it? Oh, that's right there at 3. That's right there at 3. So our local min is going to be f of 3. So there's your little bit of an algebra recap in case you forgot things about your absolute maxes and min. We're going to talk about that our x is our address, so we can write things in. Notice I didn't even write in what the y values, what the maxes were. We'll do that later, but this is a little shorthand so we can jump through it. So we'll continue thinking about the ideas of local maxes and mins, and when we come back, we'll take a look at these.